All right, we talked about chi-square goodness of fit tests. So in a chi-square goodness of fit test, you're comparing a distribution to some theoretical model. And we've talked about chi-square tests for homogeneity and independence. Chi-square tests for homogeneity are matching two or more populations distributions to looking to see if they're the same. And then a chi-square test for independence, you have one population and you're seeing if the variables are independent. So we've talked about that, but we haven't actually talked about the mechanics involved with the homogeneity and independence tests. So we're going to do that today. And we're just going to use the two examples I had already looked at yesterday, and then I'll let you do the assignment. And we'll be working on this over the next few days. It's important not to forget about chi-square goodness of fit tests. Okay? So on this one, a random survey of autos parked in the student lot and the staff lot at a large university classified the brands by country of origin as seen in the table. Are there differences in the national origins of cars driven by students and staff? So, first of all, we talked about this before yesterday, we'll talk about it again. Is this a test of independence or homogeneity? Well, it says it's a survey in the student lot and the staff lot, so that's two separate populations. So we'll say that this is a chi-square test for homogeneity, okay? All right. In part B, it says write the hypotheses. So this is going to split it all apart for us. Of course, we know that doing a test, all this is involved. When you're doing a chi-square test for homogeneity, you're just seeing if the distribution for both groups is the same, or are they different? So in this case, the null hypothesis is the distribution of car origin is the same for students and staff. And then the alternative is that the distribution of car origin is not the same. That's the only difference. So homogeneity, you're looking to see if the distributions are the same. When we start talking about goodness of fit tests again, we start putting all this all together, the biggest question I get is, well, then what's the difference between a chi-square test for goodness of fit and for homogeneity? Well, in goodness of fit, you only have one population, and you're comparing it to some theoretical model. And it's not independence because there's not more than one variable. So you have to have two or more populations to do homogeneity. Just remember that. All right, in part C, it says to check the assumptions and conditions. So we have pretty much three we need to check. Do we have counted data? We do. Counts are provided for each category. We need to see if it's random. It says it's a random survey. If it didn't, we would assume it's a good representation of car origins in both student and staff populations. But this one's a random survey, so I guess we can write a random survey of cars in each lot. And then the last one is expected counts. Now, we want the expected counts, that is a mess. We want the expected counts to all be greater than 5. Now, this is a chi-square test. Remember, chi-square is still calculated the same way. The sum of the observed minus expected squared divided by expected. All of these numbers in the table, those are all observed values. We can get a whole new set of expected values for each one of those. Okay? So you're still having to find observed and expected, and we're going to hope expected counts are all greater than 5. Now, there's two things I want to talk about expected counts. One, I have seen many a multiple choice question asked just for the expected count for a particular cell. So that means, like if I want to know the expected count just for student drivers that drive European cars, I just want to know this one. They ask that a lot in the multiple choice question. And what they do is they show you in a formula that we don't talk about in our book, but it says you take the row total times the column total, and then you divide it by the table total. Okay, so I could do that. If I wanted to find that one expected section, I could do that. Here's what I would do. I would find the row total, 33 plus 12, that's 45. For the column total, I have 107 plus 33, and so that's 140, and 140 plus 55 is 195. Okay, and then I would need to find the table total. So right now I have, just for that one, specific one that right here, that one expected count. So I would have 195 times 45, and then divide by, and I'm pretty sure 105 plus 12 is 117, and 117 plus 147 is 164. Yep. And so we get 359 for our table total. So I would divide by 359. That would be my expected count. And on the multiple choice questions, they're going to leave them like that. So I want you to be familiar with that expected count. Now, here's the good news. You do not have to go through and do that for every single expected count and then do all the work in your calculator like you did with the goodness of fit test. So that's nice. Okay, your calculator is going to do all this for you. So what we're going to do is we're going to go ahead and we're going to find the expected counts, and we're going to make sure that all of the expected counts are greater than 5. Right? But again, this is just if you want to know a specific cell, and on the quiz I'll probably ask you for a specific cell. On the test, there'll be multiple choice questions that ask you for a specific cell. Okay, so make sure that you have that idea. Okay, row total, column total divided by table total. Okay, so let's look at this on a calculator. Now here's the thing. With the goodness of fit test, we use lists, but here we have two variables, so we're going to have to use not a list, but a matrix. So if you go to your matrix menu, which is second reciprocal button, it's matrix, it's also the D button if you're looking at alpha, and you scroll over to edit, we're going to put our data into a matrix. So a matrix is always rows by columns, so we have 3 rows and 2 columns, and we're going to put in our data. Now it goes from left to right, so make sure you put them in that way. 107, 105, 33, 12, 55, 47. Okay. Now we're going to go ahead and do the test, and we'll go back and do the test again in a second to look at the numbers. But when you perform the test in your calculator, it fills in all the expected counts for you. That's nice. That means you don't have to actually calculate any of them. So go to Stat, Tests, and scroll up to chi-square test. Now it asks you observed. That's where you put the numbers for your matrix. So I put them in A, so I put observed A. And then it's not really asking you for an expected matrix. It's asking you where they want to put, where you want the calculator to put the expected values in, what matrix. So I'm just going to leave it as B because I don't need any other matrices. There's nothing I'm trying to save in there, so we're going to look at B. If you hit calculate, it gives me my chi-square value, it gives me my p-value, it gives me the degrees of freedom, which we'll talk about again in a second. But if you go back to the matrix menu, and go over to edit, and go down to B, that wasn't there before, and now all of the expected counts are there. If you notice, all of them are greater than 5. So our conditions have been met. Okay? So there's two ways you can look at expected counts. Row total times column total divided by table total for each, or you can use your calculator. All right. So now we're down to find the p-value. All right, so normally we would name the test. We've already said it's going to be chi-square test of homogeneity. Now, I briefly mentioned degrees of freedom yesterday, but we need to talk about degrees of freedom now. So if you're going to figure out the degrees of freedom, in this case, degrees of freedom are going to be the rows minus 1 times the columns minus 1. So in this case, we have 3 rows and 2 columns. So 3 minus 1 is 2, and 2 minus 1 is 1, and so 2 times 1 is 2. So I have 2 degrees of freedom. So I'm doing a chi-square test of homogeneity with 2 degrees of freedom. That needs to be included in your sentence before you find the p-value. Now again, technically, we just found all those expected values, and if I was going to find the chi-square statistic, I'd be doing 107 minus whatever my expected count was squared divided by whatever the expected count was, and I would do that for all 6 of these numbers, and I would add them all together. But your calculator is going to do it for you. So we'll go back to the calculator again. Go back to stat test and go back up to chi-square test. And this time we'll stay here. And it tells us our chi-square value is 7.828, or 828, and then our p-value is 0.019 or 0.02. So we've got chi-squared of 7 point, already forgotten, 827, or 828, and a p-value, which we want to write correctly, so we would like to write that as the probability that chi-square is greater than 7.828, 0.02. Okay? And so if we're going to state our conclusion, 0.02 is low, and so we reject the null hypothesis. So this is low. We're going to reject the null hypothesis. And so that means that we think that the distribution of car origin is not the same between students and staff. All right, so the conclusions are the same we've been talking about all year long. You mentioned the p-value, it's low or high, you fail to reject or reject depending, and then you talk about what that means in context. So the p-value is low here, we reject, so the distribution of car origin is not the same. All right, good news, we're going to do a chi-square test of independence next, and the mechanics and everything we just did is the exact same. So the only thing that's different is the hypotheses, and then, of course, in your conclusion, because you're basing it on different hypotheses. So one more. So here's our fish diet question. Medical researchers followed 6,272 Swedish men for 30 years to see if there was any association between the amount of fish in their diet and prostate cancer. So we have 6,272 people, so this is going to be a chi-square test for independence because we have one population. And this is a prospective study because they identify individuals and then follow them over time. Okay? Now in part C, it says, do you see evidence of an association between the amount of fish in a man's diet and his risk of developing prostate cancer? So that just means do the test. So we're going to do the test. So the null hypothesis, in this case for independence, is that your variables are independent. So I say fish consumption level and prostate cancer risk are independent. You could also say are not associated. That's fine too. The alternative is that fish consumption level and then prostate cancer risk are not independent. In that case, they are associated, so that's fine too. Okay, so for homogeneity, you said the distributions are the same. For independence, you're saying that the variables are independent. No association between the two. All right, so after you write the hypotheses, we should probably check the conditions. And so we have some conditions to check here. The all data is provided as counts. And the 6,272, is that what the number was? I don't think I made that up. Yeah. Swedish men is a good representation of, we're going to go with Swedish men because they didn't survey anybody else or study anyone else. And then we want all of our expected counts to be greater than 5. Now, we'll look at those in a second. Take my word for it right now that they're all greater than 5. So after we've checked the conditions, we're going to write our sentence. So because the conditions are met, I can perform a chi-square test of independence, and the degrees of freedom are rows minus 1 times columns minus 1. So that's going to be 4 minus 1 times 2 minus 1. So that's 3 times 1, which is 3. So with 3 degrees of freedom. Okay. So far, so good. All right, now we have to do the test. Now, we're going to do the test in the calculator, and we're going to find what our chi-square value is, and the probability that that chi-square value is greater than whatever it is to get our p-value, and we'll make a conclusion. But I want to mention this table. This column isn't technically a column in the table. That's the totals. You don't put the totals in your matrix. You talk about the variable. So we have fish consumption in 4 different categories, but then we just have prostate cancer. Well, for example, 14 men got prostate cancer out of 124 that never ate or seldom ate fish. So I'm missing a category. Total subjects is not a category. The other category is no prostate cancer. And so, for example, if you have 14 out of 124 that have prostate cancer, then 110 did not, right? Same thing for small or part of the diet. We have 2,621 and 201 did have prostate cancer, so 2,420 did not. Let's see here. The next one, 2,978, 2,769, and then 549, we have 42, so 507, right? So those are your numbers you would need. These are the 2 columns you want, prostate cancer and not prostate cancer. So when I put these in my calculator, I need to make sure I put those into those categories and not the total subjects, because total subjects is not a category. I don't want you to make that mistake. Okay. So let's type these in here. So we go to our matrix menu, edit. This is a 4 by 2. So we've got 14, 110, 201, 2420, 209, 27, 69, 42, and 507. So then we go to stat, test, chi-square test, have them observed when the expected and be, calculate. And we find out that our chi-square stat is 3.68, and our p-value is 0.298. So 3.68 equals 0.298. We already said there's 3 degrees of freedom. So our p-value is high. So we fail to reject the null hypothesis. And so that means we think that, circle the wrong one, that means we think that fish consumption level and prostate cancer risk are independent or not associated. In part D, it says, does this study prove that eating fish does not prevent prostate cancer? No, it doesn't prove anything. We showed they were not associated. That's it. Okay? So the mechanics and everything are the same. The only thing you have to do is identify which test so you know what the hypothesis should say. I really caution you to this because you guys keep telling me that chi-square isn't that bad because it's not. We're so used to hypothesis tests. But on the AP exam, all right, then you have, let's say it's a chi-square test of homogeneity, and you do a chi-square test of independence, and it's beautiful, and it's the best test you've ever done, and it is 4-worthy. Well, because you did the wrong test and you put the wrong hypotheses, the greatest score you're going to get is a 2 instead of a 4 because you just picked the wrong test. So make sure you're doing those correctly, okay? So when you practice today, we'll practice again some more, and we'll do a practice quiz and put kind of goodness of fit back into the mix. And then we'll be able to kind of wrap up chapter 26.